Anniversary, July 4th, 1997, Mars Pathfinder. Mars Pathfinder used an innovative method of directly entering the Martian atmosphere, assisted by a parachute, to slow its descent through the thin Martian atmosphere and a giant system of airbags to cushion the impact. The landing site, an ancient floodplain in Mars' northern hemisphere known as Ares Vallis, is among the rockiest parts of Mars. It was chosen because scientists believed it to be a relatively safe surface to land on, and one which contained a wide variety of rocks deposited during a catastrophic flood. The lander, formerly named the Carl Sagan Memorial Station following its successful touchdown, and the rover, named Sojourner after American civil rights crusader Sojourner Truth, both outlived their design lives. The lander by nearly 3 times and the rover by 12 times. From landing until the final data transmission on September 27, 1997, Mars Pathfinder returned 2.3 billion bits of information, including more than 16,500 images from the lander and 550 images from the rover, as well as more than 15 chemical analyses of rocks and soil and extensive data on winds and other weather factors. Findings from the investigations carried out by scientific instruments on both the lander and the rover suggest that Mars was once warm and wet, with water existing in its liquid state and a thicker atmosphere. For more, log on to www.nasa.gov/missions.
spacecraft should be approximately a mile above
Oh, we could in
the surface
theory
of Mars.
switch to the
There's a lot of
LCC, but
uncertainty
it may not be
from
worth
here
it.
on out.
Okay, yeah, don't change the configuration.
Correct.
Yeah.
The spacecraft should have...
Are you seeing any signal at all on the frequency analyzer, stability analyzer?
Airbag should be inflated.
That's a negative.
Rockets should be firing.
Okay, keep your eyes glued and let us know if you see anything at all, please.
I think I have 8 sets of eyes watching it, and we don't see it.
Okay, roger.
EDLCOM, EDL63.
EDLCOM.
Yeah, and FSR2 carrier spectrum shows something at PCN, not at 5 dBHz, but it might just be noise. Roger, can you concur on that?
I see same, but it's not at a frequency I would expect. It was not an extrapolation of the drift that we saw before, so I think it's probably a noise spike.
Okay, copy. EDLCOM, a weak signal is coming in and out of the spectrum.
Yes.
Roger that.
Yes. Yes.
EDLCOM has reported that a
Keep watching.
is barely visible.
Sammy, do you have an offset for that?
That's a very good sign, everybody.
I believe I have a firm signal. It's,
Okay, we've got a good strong signal now. We're seeing in a side band from the FSR1. Do you concur?
I did see a signal in the...
Tom, you did it! I can't believe it. Thank you. Well, although we're very happy up here, let's go home. We can't go home yet.
Okay, it's been roughly 1 month since the last press conference, and we continue to receive very exciting new science information that has significantly improved many of the investigations that we have on board. Some of these are due to the fact that we are staying alive much longer than we originally planned. By tracking the spacecraft, we're learning things about the interior. But also, in addition, the fact that we have this mobile robot, this rover, that's continued to operate in a robust form, that has gotten information, close-up images of rocks that are beginning to tell us a very exciting new story, and we'd like to go through that. Basically, to this point, we've received about 83% of the SuperPan. If you recall, that's the ultimate data set from the site. It's optimized by direction and lighting geometry to be taken slowly over a very long period of time. And roughly we have about 119 out of 144 supercubes of that super panorama. That's just about lossless data in every filter. We have significantly improved our super resolution data set, which is taking the same picture from a variety of slightly different camera backlash angles to get subpixel scale resolution in the far field. We've returned a significant amount of data on aerosols in the atmosphere and magnetic properties by looking at the magnets on the spacecraft. And of course, we're always tracking the rover as it goes through its paces. In that month, we've returned about 3 million individual pressure, temperature, and wind measurements on the surface. We've made about 5 alpha proton X-ray spectrometer measurements of rocks, and we've returned about 150 individual rover images as well. And we continue to receive a few million hits per day on our website, so some people are still finding this interesting. Let's go straight to the images to show you what we've been doing. The first one is the beloved rock garden. This is, as you recall, one of our highest priority science areas because there are all these nice big fat juicy rocks that are not covered with lots of red dust. And as you remember, at the end of the last press conference, we had finally gotten ourselves extricated from Wedge after hugging it and a variety of other things, gotten over to Shark, where we took an APXS measurement here. You'll see a stunning image of this area right here that Henry Moore will show. We then took 2 APXS measurements on Half Dome, shown here, one on Mo, shown here, and one on Stimpy, shown here. And you'll also see a stunning view from the rover of Stimpy that shows fluting by Wes Ward. The rover then finally decided that we had enough of the rock garden. We exited this way out, went over to the swale, and looked down in there, and lo and behold, we saw things that you cannot see from the lander because they're down in a hole, basically. And you'll see stunning views of sand dunes in that area. We came back to get Chimp, and then we were ready for our road trip back to the lander. If we can start showing the first movies, then we have, the next image. This shows the alpha proton X-ray spectrometer against a Mo here. You can see it's placed here to get that chemical composition measurement. Next one, just about the same thing in a different view, showing where we are and how we had to place ourselves with respect to the other rocks to get that measurement. Next one shows the rover up against Stimpy. Here you see the APX placed up against that rock, and you'll see a close-up image of that in a bit. Next one shows the rover after we've moved out of the rock garden and around, and we're looking down in this swale just beyond this ridge here at a whole variety of features we could not see from the lander. Next one shows the rover approaching Chimp, a nice large rock that we got an APX of. Next one shows the rover up against Chimp with the APXS deployed against that rock. Next one, I believe we start a series of 3 rover movies. Here's our first attempt on, let's see, Mo, I guess. The rover turns and actually drives up the rock a bit to get the APX. Where this is the rover actually leaving the rock garden. Here's Wedge in front, going over some difficult terrain to go around Chimp, which is shown in the background. Here the rover is moving. Here's Chimp for reference, back away from the lander and the idea is to get to the edge of that swale to look beyond it. We did that and then brought the APX up against chimp. This is a reverse pan. The idea was to leave the rock garden after we got chimp, and we put in effectively a road trip, first road trip on Mars, to send the rover back to the ramp magnet as quickly as we could, using a variety of technology commands that would minimally command it, and it would drive pretty much on its own. That has probably been circumvented by the fact that the rover has gone into contingency and is driving back to the ramp magnet anyway. It would have gone this way in the back along the ridge here and around. This area to the north-northeast is where we hope to explore in the far, far distant future. After we get done at the ramp magnet, we'll explore and move away from the lander up to this ridge a couple of 100 meters away. Here's our friend Scooby-Doo and Baker's Bench, which we'll investigate on the way to that, on the way back from the ramp magnet. In addition, we will do a drawbar pull in the area here where there's some white-colored, looks like rock underneath this soil, and try to do an APXS measurement there. We will then take close-up images of Barnacle Bill, our old friend, and trench through some of the tails. This is an example of the kind of manipulation you can do with the images, putting it on a sphere, so there's no distortion in the far field. Effectively allows you to fly around the site and look at it without hills where there aren't supposed to be hills and so on. So this has been geometrically corrected to be as if you were standing there at the surface yourself. Kind of makes you dizzy, doesn't it? But it certainly shows you the layout of the site. Okay, then the future plans then beyond the rover plans I just discussed are to continue to track the spacecraft in the experiment that will be described next, continue to monitor the weather through the fall and winter seasons on Mars, and look for surface and atmosphere changes among the surface that might have been produced by the oncoming dust storm season. And finally, just to keep track of the rover and where it goes, and continue to return that super panorama. Next to William Faulkner.
I'm leading a group doing a rotation and orbit dynamics experiment to learn more about Mars by monitoring changes in the distance between the Earth and Mars. The distance and changes in the distance are measured using the radio signal between the Deep Space Network and the Pathfinder lander. The first figure is just a schematic representation of the experiment. I don't have any image-based data to show. The Doppler data, the Doppler and range data measurements have a diurnal signature due to the rotation of Mars. It rotates about once per Earth day, and there's a minimum in the Doppler signature. I don't know where the pointer is. There it is. Over the course of a Martian day, the signature has a minimum when the lander is closest to the Earth and recedes from the Earth. So that's the spin signature. The timing of the signature tells us that the longitudinal location of the lander pretty accurately, and the amplitude depends on the direction of Mars's spin axis, the way it points in inertial space, and also on the distance from the lander from the spin axis. Over the course of time, the amplitude of the signature changes as the geometry between the Earth and Mars changes, and that allows us to infer the direction of the spin axis in inertial space. By comparing that spin axis direction as determined from Pathfinder, and as determined earlier from the Viking lander, we can determine the rate of change of the direction of the spin axis direction. Anybody who's played with a top and spun it on a table knows that it's pulled by the Earth's gravity around in a circle, in a precession motion. And similarly, the Earth's spin axis precesses due to the torque of the Sun around the Earth. So the Earth's spin axis rotates in direction around the Sun once every 26,000 years. Mars rotates much more slowly. By measuring the spin axis and the spin axis direction with the Pathfinder data and comparing it to the Viking data and determining this precession rate, we learned something about the interior structure of the planet, because the speed it rotates depends on how the mass is distributed inside. So the next figure shows sort of an enlarged cutaway of Mars, and if we make a simple model of Mars, there would be a core and a mantle and a very thin crust. And to determine the density of the core and the density of the mantle, we'd like to know four things. We'd like to know the mass and size of the core and the mass and size of the mantle. From previous measurements from Viking orbiters and other ground-based astrometry, we know the size of the planet and we know the mass of the planet from the gravitational pull of orbiters around Mars. By measuring the precession rate, we know the moment of inertia of Mars, something about the radial distribution of mass inside. So that gives us a third parameter out of this four-parameter model. We'd like to know a fourth parameter, and we don't have that yet. We hope to eventually learn a fourth parameter, the size of the core, by the influence. If the core is fluid, then it will affect the nutation of Mars. Back to our top analogy, if the top's spinning, if you don't spin it exactly right, it'll kind of nod around, and that's called nutation. If there's a fluid core rather than just a completely solid mantle and core, that nutation will be different. Just like when you spin an egg, if the egg is hard-boiled, it will spin pretty uniformly, but if the egg is raw, then it'll wobble very differently. It's not quite as dramatic an effect as if there's for the Earth, which does have a fluid core, or for Mars, because the core is much smaller, much less viscous. But we hope that through an extended period of tracking of the Pathfinder data, if we can get two-way Doppler measurements back again, to measure the effect of a fluid core if it's there. With the three parameters, we can say something about what the interior structure is like if we bound the possible compositions based on analogy to Earth or analogy to the SNC meteorites, which are found on Earth but thought to originate on Mars. If the composition of the mantle is something like the Earth or these meteorites, somewhere in that range, then if the core is as dense as possible, if it was solid iron, then this moment of inertia measurement says the size of the core can't be less than about 1,300 kilometers in radius. This is out of the planet's radius of 3,400 kilometers. If the core is made out of something less dense than iron, if it's a mixture of, say, iron and sulfur, then it would have to be a little bit bigger, but it probably couldn't be bigger than 2,000 kilometers and still have a plausible mantle composition. If the core was going to be bigger than that, the mantle would have to be composed of something very different than the SNC meteorites or the Earth. So this determination of the moment of inertia using the Pathfinder data in combination with the Viking data constrains the allowed range of models for the interior Mars. So that's what we know so far, is given some reasonable modeling constraints, we can kind of bound the size of the core. It's really dependent on future measurements, hopefully from Pathfinder, but maybe from future measurements to determine this fourth parameter that will actually give us the core size itself. Besides trying to learn about the interior of Mars, we're also interested in the interactions of the atmosphere and the ice caps of Mars, because they change the rate at which Mars spins around its axis. The Earth's spin rate changes mostly because of the interaction of wind and surface features. As the wind pushes on the mountains and as the wind speeds increase and decrease with the seasons, then it changes the rotation of the Earth. On Mars, it's controversial. We expected that its rotation would mainly change because the amount of atmosphere changes between winters and springs, because in the winter, in the northern winter, atmosphere condenses out at the ice caps. And so just like an ice skater pulling in her arms, rather than have atmosphere spread out at the equatorial bands, it will condense onto the ice caps and the planet will speed up a little bit. So there's been previous determinations of this change in speed of rotation from the Viking data. We can see in the Pathfinder data a slow change in rotation over the few months we've got now, and we can determine that short period change very accurately. The long period rotation rate change is better determined for now from the Viking data, and it agrees pretty well with a model for the change in the atmosphere as measured by the pressure and condensing at the pole. So we think that confirms that it's not an interaction of wind speed and atmosphere, but it's this change of mass distribution that changes the rotation rate. As we get a little longer Pathfinder Doppler arc over about half a Martian year, we expect it to determine that change in rotation much better than we know it now. So we're really looking forward to more Doppler data. And I'll turn it over to Hank Moore.
Can I have the first slide? I think of the rover as your field geologist, and she's been up there on Mars doing lots of things, and she is patiently waiting now for Jennifer and her crew to bring back the lander so she can tell us more about Mars, and she appreciates their effort. What I'd like to talk about, this is a plan view. This is the lander here with the pedals, the ramp, and the black lines are traces of where she's been. The little squares here, a meter on an edge. This is Yogi, and I'm going to show a picture of Cabbage Patch, which is roughly in here, and then over here with a picture of Shark and a little rock near Shark. Can I have the next slide? What I call this is the problem of the pebbles. And the rover sees these pebbles very, very well because she's close to the ground and makes her spatial resolution very high. And if you look right in here, you'll see this round pebble. And so one of the questions is, why is it round? Another question is, where did it come from? And then how did it form? And things like that. There's some other ones here, like here, and I think this is one over in here. But anyway, there are a number of these little pebbles around. And on Earth, some of the postulates, the geologists use what we call the multiple working hypothesis when we address a problem and we have a set of observations. And so one of the postulates for the origin of these little pebbles is that they, well, before I forget, this is a trench that was dug by the rover rear wheel, and you can see little half-centimeter size lumps, or they may be either little granules, and this thing is about 4 centimeters. But anyway, we use the multiple working hypothesis, and one of the postulates is that this is a pebble that was rounded during the catastrophic floods as they came down Aries Valleys or one of the other valleys, and were deposited directly from one of the floods. Another one is that maybe it was formed on a beach, and it was a rock, originally an angular rock, and the wave action moved it back and forth so that it became rounded. Another way you can get rounded pebbles is through transport by glaciers. And then another postulate is that they're glasses formed, they're impact melt glasses that were formed during impact cratering, melted, ejected into the atmosphere where they formed droplets or spheres, and then deposited at the site. And then another possibility is that some kind of a spatter from a lava flow. This will give you an idea of how complex the geologic issues are. Another suggestion was that maybe there are concretions, which are little rounded objects that form in sedimentary rocks by cementation around small grains and inhomogeneities in the rock. And another idea is that these things somehow happened before the flood, and that they are actually pieces or something that's fallen out of a larger rock, like a conglomerate, which is a gravel that's cemented by calcium carbonates or fine-grained clays or something like that. And then the other possibility is that some combination of all of these things. Could I have the next slide? What I would like to propose is that these things are really come from rocks. This, I think I can see it, the little pebble is right there, the one we saw in the, this is an imp image, and there's the rover, there's the little pebble that we saw, it's about 4 centimeters across. If you look right in here, you'll see a rounded object in here, and it may be a cobble that's in this rock called lamb, and lambs is about a foot across. May I have the next slide? Next, I'd like to go to Shark, and this is a lander camera image of Shark. You see that there are a couple of lumps here. There's a pretty good lump in here. May I have the next slide? And the rock we're going to get a real good look at is this little rock in here. It's probably about 20 centimeters or so across. Shark was about 70 centimeters across. Next. this is a picture of shark. In particular, that little nubbin I showed you earlier on shark, this could be a rounded fragment in a conglomerate. And if you look at the whole surface of shark, you see lots of knobs and lumps and things like that. There's a lump, a couple lumps there, a lump there. So this could be a conglomerate that was formed elsewhere and then brought into the Aries site by flood. The next place where we're going to look in a minute is this smaller rock right in here, and we'll get a close-up of it. Next slide. This is an interesting rock, and it suggests that we are, in fact, dealing with conglomerates. If the sun is kind of shining up above, so this thing is a little depression, which I call a socket right there. There's a bigger socket here, another socket, a small socket, all different sizes of sockets, which is a common thing for conglomerates to have. And then if you go over in here, you see something that looks different. These look like little spheres. And what they are, I think, are little small pebbles in this conglomerate. And then there are a number of them, a string of them over in here. And so I think we're looking at conglomerates, and afterwards, those who wish to, I brought one from Utah near Soldier Summit from the base of the Price River Formation, which is about, something 20, 25 million years old. The significance of this observation, and it's only possible for the rover to see in this detail because she gets up close to the rock, she carries her resolution with her, and she carries her stereo base with it. The previous IMP images, you couldn't see this detail at all. So she's a real good observer, and she's trying to give us information to come up with some important conclusions about Mars. One of the points that should be made is that all of the rocks that we see are not volcanic rocks. They're not lavas or lava flows that have congealed, or they're not some kind of a magma that formed at depth and was brought to the surface. Some of them may be, but not all of them. Another thing is that these conglomerates may be ancient sedimentary rocks that were deposited from previous streams and floods, and that in the past we had climates with sufficiently high pressures so water could be present at the surface to produce rounded pebbles and cobbles and things like that. And this would be in addition to the ones that we observe as a result of the Aries floodplain. So there'd be an earlier version. Another thing is that this was postulated to be a grab bag sample site. And it looks like that postulate is true because we see conglomerates, and then there are other rocks like Stimpy and Hassett, which appear to be hexagonal prisms, and hexagonal prisms form by cooling of lavas or rocks that were hot. And so it's going to take a long time to sort all of the things out that we're seeing, but things are really looking interesting and exciting. Now I'd like to turn it over to Wes.
Thanks, Hank. You've had a pretty good briefing on the geomorphology of the landing site from the science team in terms of water being the dominant agent that's carved the surface there. I'd like to make 2 points this morning. First, there is another agent at work, and that is the wind. It has created or modified some landforms at the medium and small scale. And because the water is no longer there, the wind probably is a dominant agent shaping the Martian surface at this moment. The other thing I would like to make is, the other point I would like to make is we think we've solved a little bit of a mystery that we had from the Viking times, and that is from orbit we were able to see a lot of dune features on Mars, but when we got down to the Viking landing sites, we didn't see such features, and we didn't see characteristic sediment, sand sized particles that make up dunes on Earth. So I'll try to address both of those. If I could go to the first image, please. This is a part of the Superpan sequence showing some old friends again. Here's Yogi up in through here. I want to spend just a minute right in this area talking about Barnacle Bill. And again, you'll remember we've talked a little bit before about these depositional tails, these so-called wind tails behind some of the rocks. And then you may be able to also make out a little bit of a moat in front of Barnacle Bill. And the presumption is that we're looking at deposition of fine sediment like a powder downwind of Barnacle Bill. And the wind direction is just about where the arrow is in this image. Just as nature abhors a vacuum, it also abhors disequilibrium. And so again, what's happened here, the rock offers a pretty rough flow field, if you will, to the wind as it passes by. And so within that geomorphic process, sediment is deposited behind here to then more or less smooth out the airflow associated with this rock. Next image, please. This is a map view of the landing site with some red arrows on there that you can see, done by our colleagues from Arizona State University. And what these represent are interpretations of the wind directions as we would map them from these wind streaks. And what you should be able to gather from this image is that most of the streaks point off to the lower left or to the southwest. And our interpretation here is that the effective wind at the landing site comes from the northeast. This matches what we've seen from orbit, from Mariner 9 and from the Viking orbiters in terms of the light and the dark streaks associated with craters are also pointing off to the southwest. Next image, please. I want to talk a little bit about what a sand dune is and how it works. In the case of Earth, we're talking about sand particles, sand grains, on the order of a millimeter and a little bit smaller than that. Typically on Earth, it's quartz and feldspar. For the purposes of this discussion, we aren't going to make any assumptions about the nature or the composition of the material. But when I refer to sand, I'm referring to particles on the order of a millimeter or so. In the terrestrial case, we're looking at two dunes here, a dune that's called a Barkhan dune up here, and then down here is a ridge dune. The blue arrow shows that the direction from which the wind blows to which it's blowing. So in this case, it's lower left to upper right. In terms of the actual activity of the dune, think of the proverbial model of the lemmings marching off to sea. And what you'll have in this case is sand grains hopping along the windward face of the dune here, and then avalanching down this steeper side that's called the slip face. Next image, please. So here we have the rover Sojourner, our field geologist, visiting the so-called mermaid dune. And Sojourner is facing towards the lower left and is looking upwind, if you will. So here is this face along which sand grains will hop. There's the crest line of the dune roughly along in through here. And then back on the back side, this is the so-called slip face or avalanche side. This image is really neat because we have all three of the rover's wheels on a given side doing some digging inside of Mermaid. So here we are just at the upwind side of Mermaid, right now at the crest line, and then finally on the slip face. Next image, please. Here are two images. The upper one is from the rover looking upwind from Mermaid. So again, here's a trench in here that one of the wheels has made, and we're moving off the dune back into the ordinary surface. And here's another hole over in through here. In particular, we'd like to go to an enlarged view of this segment right in through here, and you should be able to make out the particles that Hank referred to as granules, grains of sediment, on the order of a little larger than a millimeter, down to and below the limit of resolution. So it looks like in digging inside of Mermaid, we've come up with at least two sizes of sediment. And again, you can see a small range in through here. Next image, please. This is a feature called Jenkins. This is a dune imaged by the IMP camera. Jenkins is sort of down in a little hollow. The height of the feature is less than a meter, maybe a foot or so. And then its long dimension is about 2.5 meters. And this looks typically like a Barkhan dune on Earth, where again we would have the saltating windward side over and through here, and then a steeper side over here that would be the slip face. Right along in through here, just at the crest line, we have a rather interesting feature, reminiscent of what we saw at the Viking 1 site associated with some sediment at the rock Big Joe. And what we're wondering here is perhaps is this evidence of a little bit of a crust on Jenkins, and the material sediments calving off, dropping down this side. The inferred wind direction then in this image is from the left to the right. Next image, please. This is another rover image. Again, she's an excellent field geologist. In the background, you can see the Twin Peaks. And here we're looking at some dune features. Again, not very high in terms of height above the ground, but certainly again on the order of several meters long. The inferred wind direction in this case is from the right to the left. So here we have again the accumulation side, if you will, where material sediments are hopping along a crest line in through here and a slip face over on this side. Next image, please. We'd like to contrast those for you with what we saw at the Viking sites, and these were landforms that we referred to as drifts, and we have done that because these landforms don't seem to have any true slip faces associated with them, and so what we believe in this case, we're probably looking at again very fine powder dust-like sediments that have been deposited in the lees of some rocks, perhaps, in this case by winds moving from the left to the right. And perhaps these features were cemented because we're starting to see what looks like bedding features exposed here, as if these drifts have been eroded, and perhaps by a wind moving in the other direction. But regardless of that particular interpretation, the features that we see at the Pathfinder site are markedly different from what we've seen at the Viking sites. Next image, please. This is a close-up that Matt alluded to earlier of one of the rocks. This one is Mo, and we're looking at two faces of Mo. This face over here tends to face off in the easterly direction, and this one a little bit more to the north-northeast. What we'd like you to notice about this one, again, is the fluting on the surface of this rock, and this is a texture that we see in deserts on the Earth where the rocks have been abraded by wind that's also carrying sediment. This particular face over and through here, again facing off in the east, and this one in the northeast, have orientations that are similar to the orientations that we see of the sediment tails and the dunes at the landing site. I'll show you that in the last slide. Correct. Okay, so again, here's the lander and the rover in a view from a map done by our folks at Ames. Here is Mermaid Dune again, the crest line. In through here, the accumulation face where sediment is hopping, and the avalanche face or the slip face over on this side where the grains then tumble down. And the inference in here is that the wind moves from the northeast blowing to the southwest. You'll remember the images that we showed you earlier on about the sand tails, again showing wind moving from the upper right to the lower left. The rock that I showed you a minute ago, Mo, roughly off in this direction, also shows abrasion from wind coming roughly from the northeast. I think that's my last slide. So the 2 points I would like to leave you with today is that again the water is all gone. The wind is indeed quite an active agent. Hank and I have a sort of a running discussion about the so-called smoking gun. That is, he won't believe that there is sand on Mars up until Sojourner goes up and scrapes it, rubs it through her fingers, proverbially. As far as I'm concerned, there is a gun, the barrel is hot, I smell smoke, there's a round discharged, and Colonel Mustard's fingerprints are all over it. So a number of us do believe that we have evidence now for sand at the landing site.
Well, we all know that the Ayers Vallis landing site is a geologist's paradise, but the weather isn't too shabby either. About the only thing worse than giving you a day-old weather report is going to be the 11-day report that should be up on your screen now. The last time that we received weather data from the Pathfinder, the temperature was minus 54 degrees Fahrenheit at 8:45 a.m. local solar time, peaking to a high temperature of 8.6 degrees Fahrenheit when the last data was returned about 2:30 p.m. that afternoon. The minimum pressure was 7.05 millibars and it occurred at 10:06 in the morning, with a peak pressure of 7.26 millibars that occurred about a little afternoon. This 2% variation in pressure is consistent with the background global dust opacity of about 0.5 to 0.6. Jim Murphy reports that the winds are light and variable, coming from all directions and rotating around in their usual counterclockwise fashion. Pathfinder continues to be experiencing typical late summer weather-like conditions, but Bob Haverly says that we should start expecting some weak synoptic scale systems blowing over the Ayers Vallis outflow channel as we have passed the Mars equinox about 30 days ago and we gently move into the northern fall. As Matt said, in the past 27 days of operation since the last press briefing, the ASI Met instrument continues to return a massive amount of useful data. We've gotten the 3.1 million individual weather samples, bringing our total for the mission to an unprecedented 8.5 million samples. Could I have the next slide, please? I don't seem to have the mouse is appearing there. What we can see here is a plot from Sols 55 through the last data received on Sol 82, and you can see the general increase in pressure. And this increase in pressure is as the frozen CO2 ice cap and the South Polar Cap starts to recede, releasing the CO2 into the atmosphere. And it's a little bit too early to expect any significant expansion of the North Polar Cap to reduce the mass of the atmosphere on Mars. Just to remind you that pressure is nothing more than the total weight of the atmosphere, the force provided by that on the surface. And so Mars is pretty neat in the regard that this is a massive increase in the amount of material in the Mars atmosphere. The two connected lines here are two 24-hour sequences, and you can kind of see the diurnal and semi-diurnal amplitudes of pressure. Could I have the next slide, please? Before I go on, we should expect the maximum pressure to peak at about January 22nd, 1998, and we fully expect to have an operating spacecraft at that time. I think Jennifer and her team have done a spectacular job thus far, and we fully expect that we'll get communications back. As I mentioned, we had the two 24-hour sessions. As you can see here in the red is the Sol 55 through 56, and in the blue above is the pressure signature for Sol 68 through 69. You can see the general increase in pressure during that period of time, and you can see the diurnal and semi-diurnal signatures of the tidal amplitudes. You can see some pretty unique features, and we are calling these features dust devils, and they're a drop in pressure, and we notice some wind vorticity around the landing site. On Sol 66, we tried to image these so-called dust devils and did not see anything really unusual. And also on Sol 66, we didn't pick up any unusual measurements that we would have called dust devils. Could I have the next slide, please? As I said earlier, we think we should be entering into the season on Mars and when we should expect a frontal passage, and you can see here in the blue and green Sol 79 and 80, and you can see the pressure minima occurring a little bit before 10 in the morning. But on Sol 81, we see a dramatic increase in pressure at that same period of time. And this would be a signature for a synoptic scale system passing over the landing site. Could I have the next slide? And we can also see this in the temperature signature. In red and blue, hidden behind here is the temperature fluctuations during that period of time. And you can see that the amplitude of those fluctuations are quite large. But when you come to Sol 81, those fluctuations have been drastically reduced, and the mean temperature has dropped by about 5 to 6 degrees. So we believe this is the first evidence that the shift in seasons at the particular landing site, and we should expect some more changes into the future. Can I have the next slide, please? That is the end of it. If I could get your attention up here, this is the top of the atmospheric structure meteorological experiment mass, and you can see the wind sensor up here, the descent thermocouple, and the top mass thermocouple where we present most of our data from. And here's the windsock provided by Rob Sullivan and Ron Greeley from Arizona State University. And its intent was to measure the vertical profile of the wind at the Pathfinder landing site. And as you can see, this device is quite sensitive to atmospheric currents around the landing site. Unfortunately, the wind at the Pathfinder site has not been cooperative. The strongest winds that we have recorded have been in the early morning hours when it's dark and the imager can't image the camera. And so most of our images of the windsocks throughout the day are showing them dangling straight down as they are now. But there is some hope that this will change as we move into fall. Justin Mackey put together a nice windsock movie, and if you want to, we can see some of just the slight motions of the windsocks as this windsock movie plays through. And I'll invite you to come up to the podium after the press conference. You can see for yourself how sensitive these windsocks are and what little breeze must be blowing by at the Pathfinder landing site. So what should we expect in the future when we regain contact with the spacecraft? Well, finally, I can confidently say that we're not going to just see the same old weather pattern. I think we'll start seeing a lot more of these storm systems moving through the area. We should expect the pressure to continue to increase until around January 22nd. The average temperatures should start to decrease. We should also see wind speeds pick up, and hopefully we'll get a lot of good data from the windsock experiment to where we can characterize surface roughness and the shape of the wind profile. We should also expect the semi-diurnal and diurnal components of the pressure amplitude to increase as these winds start lifting dust up into the atmosphere. And this is just a hunch, and I don't want to send the MGS aerobraking team into a panic, but in 2 to 3 weeks we might want to expect some sort of global scale dust event, or at least a pressure signature from that. The Viking Lander 1 in 3 out of 4 years experienced such events, and no reason to not expect the same thing at the Pathfinder site.
Okay, we'll go to questions from the media in just a minute. First, a couple of announcements. I wanted to remind you about the websites you can visit for more information. We have a news media site at www.jpl.nasa.gov/MarsNews. The Mars Pathfinder has a homepage that's accessible from mars.jpl.nasa.gov. And NASA also has a planetary photojournal, which is a comprehensive repository of images from Pathfinder and other missions, and that's at photojournal.jpl.nasa.gov. Also, I wanted to mention, apparently during the briefing there are some satellite problems with the feed to the rest of the country, and we're currently looking into possibly replaying this briefing later in case portions of it haven't come through to all users. With that, I guess we'll start with questions here.
Hi, Jeff Michael from KBC TV. Dr. Moore, you said you were excited about something during your presentation. Dr. Ward, you talked about a smoking gun. And you've all presented something pertaining to your disciplines. Would one of you bring all of this together for those of us in the unenlightened media and tell us what is the most exciting conclusion from what you have found thus far?
All right, I'll summarize. From what you've heard today, we have first evidence that Mars is a differentiated planet. That is, it has a core, a mantle, and a crust. And until this point, it could have been just this ball of rock that was all mixed up. We have very strong evidence that there are water-worn conglomerates on Mars, which requires liquid water to be stable with the atmosphere. And if that's an old rock, that suggests without question that the environment on Mars was warmer and wetter in the past, to the point that liquid water was stable with the atmosphere. And as you know, that's the one requirement for life. That is tremendously exciting. And until we saw this rock up close, I would say that there's been quite a bit of argument in the science community as to whether Mars had a warmer and wetter past. We've never seen sand from the surface of Mars before. We've been at 2 sites, the Vikings 1 and 2, and all we saw was dust and drift material. Sand-sized particles are distinct from dust. They're millimeter-sized grains. They're much larger, and they move in this saltating, hopping fashion. They're not just blown around in the atmosphere. They never get up above this high. Okay, we have, I would say, unambiguous evidence that sand grains exist on Mars. That says something about the environment in which they weather out and form. And finally, barometer rising. It's starting to get cold. Plan for autumn on Mars.
The significance of the sand, once again, is what?
That we never saw particles like that from the surface. We implied that they existed from Viking orbiter images, which showed these sand dune type faces, but we've never seen them from the surface on Mars. It requires weathering, primarily physical weathering, to get grains down into that millimeter size, okay, as opposed to chemical weathering, which gives you this really fine-grained dust that just drifts all over the place.